We're going to take a look at a hypothesis test for a difference of proportions. When we're working with two proportions, our null hypothesis is always that the two proportions are equal. But we could also write this hypothesis as P1 minus P2 equals 0. And so this is why we refer to it as a difference of proportions. Continuing with the idea of using a theoretical distribution, we have now a standard error formula. This one is a standard error for a hypothesis test. It is slightly different from the standard error for a confidence interval. Here we have, notice, just a single p hat that's repeated in all of these. That's not a p1 hat and a p2 hat. We're not talking about the individual proportions from the two samples. What we're actually talking about is what we call the pooled proportion, which is if we take the total successes, where by successes I mean whatever it is we're counting, and we take all the successes from both samples and pool them together, and I also add my two sample sizes together so that that's also the pooled sample size. This is what we call the pooled proportion, and under the null hypothesis, the two proportions are equal. And that's why under the null hypothesis, it makes sense to go ahead and just combine the two data sets to make one big one. Now, a few important things to note about this formula. One is that we have links in Blackboard you can use. So on homework, you're going to use a Visualize Applet that we have a link to in Blackboard. We'll see where that is when we get into our first example. Also, on tests, you won't have access to that applet, but you will just be given a standard error calculation. So you will not be expected to use this formula at all. You are not responsible for this formula. We're providing it just because it does offer a little bit of insight into the calculations, especially if you're a little bit mathematically inclined and you find some comfort in the formulas to start with. So based on this standard error, we now have a z-statistic, which follows the same form we've been following for all of our z-statistics. Sample statistic minus null parameter. Our sample statistic, if we're working with a difference of two proportions, is always going to be p1 hat minus p2 hat. And the null parameter is what p1 minus p2 is equal to under the null hypothesis, which as we can see up here is equal to 0. And then that standard error really comes from this formula we just talked about, or it comes from that standard error calculator that we have a link to in Blackboard. So when we put all of this together, we get a simple formula for our z-score. It's p1 hat minus p2 hat minus 0, which we don't have to write, and then divided by the standard error. So let's put all of this to some use in an example about smoking and pregnancy. We're interested in addressing the question of whether the proportion of successful pregnancies is lower for smoking women than for non-smoking women. And we have a bunch of values here that are counts from a study. So let's state our hypotheses first. Our null hypothesis is that the rate of successful pregnancies, or the proportion of successful pregnancies among smoking women, is the same as the proportion of successful pregnancies among non-smoking women. Our alternative hypothesis is that the proportion among smoking women is lower than the proportion among non-smoking women. And we could write each of these hypotheses as a difference of proportions also. PS minus PN equals 0. PS minus Pn is less than 0. It can be important to write the alternative hypothesis this way so that we can tell whether we have a left tail or a right tail test, provided that we stay consistent in the order of our subtraction when we calculate our sample statistic. So this should be a left tail test, and the way that we're going to make sure it stays a left tail test is by calculating our sample statistic as PS hat minus PN hat, not in the opposite order. So getting to our sample statistic, let's calculate each of these individually. My estimate for the proportion of successful pregnancies among smoking women comes from our data, and that is 38 out of 135, which comes out to be 0.281. Our estimate for the proportion of successful pregnancies among non-smoking women is 206 out of 543, which comes out to be 0.379. And now, staying consistent in my order, my sample statistic is PS hat minus PN hat, which comes out to be negative 0.098. Now, I'll mention it would have been fine to subtract in the other order as long as we stay consistent with that in all of our statements, including our hypotheses. Okay, at this point, we'll go ahead and calculate standard error using the link in Blackboard. So let's go ahead and see where we can find that. From Blackboard, there are two places we can find this link. One of them is in the item for section 6.3. We have a link in this description, standard error applet. The other place is if I look over on this menu to the left and scroll down, under external links you'll see this SE calculators. That's standard error calculators. They don't both take you to the exact same page. If I click on SE calculators, you can see that you have links to various different calculators, and I would want to look up the appropriate one, SE for the difference of sample proportions, and click on that. If I go straight from Blackboard in section 6.3, it takes me directly to the standard error calculator that I want. Now, I'm going to go ahead and stick with this default of counts as my successes. Again, the successes in this case is successful pregnancies. We call it successes even if it's counting something that doesn't sound like it would be a success, like an incidence of cancer or a worsening of a tumor or something like that. Successes is the word that we use in statistics for whatever it is that we're counting for our proportion. So I'll enter my counts for sample 1. That's 38 out of 135. And for sample 2, that's 206 out of 543. And I do want a standard error for a hypothesis test. The two standard error calculations do differ slightly from one another. So make sure you select the appropriate one. And I have my standard error down here as 0.04616. I'll go ahead and take all decimal places of that because it's just not that hard to work with. Now for my Z statistic, recall we have this nice formula. This is going to be a really easy calculation because I already have both of these quantities calculated. My PS hat minus PN hat is negative 0.098, and my standard error is 0.04616. So I get a z-score of negative 2.123. We'll go on with this hypothesis test in a moment, but I'm just going to come back to our standard error calculator and point out that if I had selected proportions instead of counts, the interface doesn't look any different, but I need to enter those proportions that I calculated, 0.281 and 0.379, and compute. We can see it comes out to be essentially the same. It differs in the 10,000ths or 100,000ths place just because we had done a little bit of rounding on those two calculations. But if you're given your information as proportions instead of counts, don't think that you have to back calculate the counts in order to use this calculator. To complete this hypothesis test, we will need to mark up a normal distribution curve and find a p-value and then state a conclusion. So we're looking at a z-score of negative 2.123, which, if we think of this standard normal distribution as being centered at 0, that would be a little bit more than 2 standard deviations to the left of the mean, which means we're getting definitely into the tail, but not really far into the tail. And everything to the left of that we want to shade. Because we remember that this is a left tail test. Now let's go into StatKey and find our p-value. Since we're talking about a test for 2 proportions, we are looking at normal distributions here. So for theoretical distributions, I'll go to Normal and select Left Tail and replace this boundary value of negative 1.960 with my z statistic of negative 2.123. I can see now that I get a p-value of 0.017, and I can look at this curve and look to see if the shaded region that I drew is pretty close to what StatKey shows. So it looks pretty reasonable. Coming back to my curve now, I'm going to say that my p-value is equal to 0.017. So using the scale that we generally use if we are not given a significance level, we would say that this is definitely strong evidence against the null hypothesis in favor of the alternative hypothesis. We'll work that into our conclusion in the next step. Strong evidence is something substantially less than 0.05. If it were much smaller than this, we might call it very strong or overwhelming evidence. Now what we have strong evidence of is our alternative hypothesis. If we look back at our alternative hypothesis, we see it was that the proportion of smoking women who successfully get pregnant is less than the proportion of non-smoking women who successfully get pregnant. So we have strong evidence that this is true, and we want to state this in context using non-technical language. So putting this in words, we can say that we have strong evidence that the proportion of women who are trying to conceive, of all women trying to conceive who are successful is lower among smoking women than among non-smoking women.